Hello everyone, and welcome to Energy, your first physics topics of your GCSE level content. Today we're looking at Lesson 1 in your energy booklets, Energy, Stores and Systems. Before we get going, I want to make sure that you have everything you need. So you will need your paper that you're writing on or the copy of your booklet if you're able to print it out, as well as a regular pen, a feedback color pen, and for future lessons in energy, you will need a calculator. Make sure you put your phone away so it's not a distraction for you, and we'll be ready to begin. So as any lesson starts, we'll start with our knowledge check. Since it's the first topic of a unit, it'll be simple true or false. So pause the video, answer all these questions as true or false, and we'll get going with the answers in a minute. Over the answers now, switching to your feedback color so you have all the correct answers in. The unit of energy is the joule. This is true. Things use up energy. This is in fact false, and we will be talking more about that in today's lesson. Electrical energy flows through an electric wire in a circuit. This is true. Hopefully you remember from year 8. An object at rest or not moving has no energy. This is false. Even if it is not moving, it can still have some energy. Energy and force are the same thing, also false, which we will talk about some more in this lesson. Energy is lost when we burn wood, is false. Friction is a type of energy. This is false. Friction is a force, not a type of energy. And at the end of this lesson, I will understand what energy is. This is actually false, which we will talk about later on. All right, but if you've said true, you'll understand more about energy. Yes, that will be acceptable. So, what is energy? So, reading through this paragraph here, energy is a term we use in everyday language, but in science, it does have a very specific meaning. All right, the simple answer, we don't actually know what energy is, what makes energy work. We just know how it does work. All right. Richard Feynman said, "It is important to realize that in physics today, we have no knowledge of what energy is. We do not have a picture that energy comes in little blobs in a definite amount. It's not the way. Energy is what we call an abstract thing that does not tell us the mechanism or the reason for the various formulas." So the fact energy is an abstract, you might remember from English class, the word abstract, or from art, means not specified or not clear as to what it is. So that abstract thing, it's not specified. It's something that we have an idea of, but we can't quite name. So energy, in the knowledge we have it, can be described as a mathematical concept or a mathematical idea. So it is a number that we use. So energy is a number. So energy is needed whenever anything happens. So for example, lifting an apple, a car accelerating or going faster, boiling a kettle of water, an electric current flowing through a wire. All of these things are something happening, which is a form of energy. I want you to think of something that you do on a regular basis that requires energy. So when we look deeper at these situations, at the boiling a kettle of water, anything, that each one involves a force acting on something. Hopefully you remember from previous years that a force is a push or a pull. Sometimes it can cause something to move, but it doesn't always necessarily need to make something move. But a force is a push or a pull. All right. So we're talking about energy, we're talking about forces. Work is involved with all of this too. So what is work? Again, we have an everyday understanding of work, but in physics, it goes a little bit deeper than that. In physics, work is done whenever energy is transferred or moved from one place to another. So whenever energy, for example, goes from your muscles into your pen to make your pen move, that is a form of work. Another form of work could be simply lifting an apple, anything like that. Could be the engine running in your parents' car to make that car move. All right? Whenever that energy is transferred. And remember, energy requires a force. Right? So that energy is something moving due to a force. So whenever that energy is transferred, gone from one place or one form to another, we call that work. All right? So it could be, again, that force to lift an apple or push the car. The electromagnetic force, remember, the electromagnetic force is the force that we work with electrons and protons. And protons. That positive and negative force is that electromagnetic force between the water molecules in the kettle. Because you hopefully remember from year 8 that water molecules are dipoles or are polar molecules, so that positive and negative are pushing the electrons in a wire. It's quite confusing, I know. I would like you to watch this clip here. It will be linked below. Watch this clip and come back to this video. So hopefully you've watched that clip now, and a lot of you will likely be, that doesn't make any more sense now, miss. So the biggest thing to remember, energy is just a number, okay? But the overall amount of energy, the overall number can't change. It just gets shifted around by doing work. So how I want you to think about energy is that it is the total energy doesn't change. There's always the same amount of energy in the universe. It only changes form. And this changing of form, the fact that the total energy doesn't change, it only changes form, is what we consider the law of conservation of energy. All right, I want you to pause now, take it all in, and I want you to write some summary notes of what we've just talked about in your books. Hopefully you understand everything we've just talked about. If you are struggling, make sure that you do go back or rewatch it, or email your teacher for some help. So, law of conservation of energy. Energy is a property of the universe, which can be given a numerical number. So, energy is everywhere in the universe. Some places have more, some places have less, but it is throughout the universe, and we see that energy behaves the same way no matter where in the universe it is. And it's given a numerical value or a number. All right? This numerical value never goes up or never goes down. So if we add up all the energy in the universe, it will always be the same. So that doesn't change. And that's essentially what the law of conservation of energy is. So if we take a chunk of this energy, so if we can compare it to a pie, if you take a piece of this pie and say the whole pie is all the energy, we take a piece of it and put it in a box, put it into what we call a system, the amount of energy in that system, again, won't change. It will always be the same within that piece, unless some escapes the system, but then it's not a complete system anymore. So that amount of energy in that section, in that defined area will never change. All right, so that's what we mean by this numerical value must be the same before something happens and after it happens. So I just compared energy to a pie. Now let's think about it as money. If you went shopping, you go into the shop, you see some chocolate you really like, and you see it's £5. You have £10 in your pocket. Can you buy that chocolate? Could you buy a house with that chocolate? Or with that £5, with that £10? No. So you could buy some chocolate for £10, but you couldn't buy a house. In the same way, if you had 10 joules of energy stored in your muscles or stored however it needs to be stored at that moment, you could lift the bar of chocolate, because it doesn't take 10 joules to lift that, but you couldn't lift a whole house. All right, you would need a lot more energy to do that amount of work. So if you spent £5 on the chocolate, it's a really posh chocolate bar, and you handed the person behind the till a £10 note, you would expect £5 in return. So you'd have £5 worth of value in your chocolate and £5 in change, in cash. All right. It works the same way with energy. If you have £10 or 10 joules of energy stored in your muscles, you use £5 of it to lift it, 5 joules of energy to lift that thing, that bar of chocolate, you still have that 5 joules of energy in your muscles. And there's 5 joules of energy now stored in that chocolate bar. So when something happens, energy is being moved or it's being transferred. The energy is moved, it's transferred from one place or one, what we call store, to another. So wherever we have that energy being held, it's that store of energy. So in your own words, I would like you to write down the law of conservation of energy. Take a minute, go back, in your own words, try to write down the law of conservation of energy. So now that you have now that you have it written down in your own words, I'd like you to add to it, and we'll write it down in the official language that it needs to be. So the law of conservation is energy can not be created or made or destroyed, used up. It can only change form. So that is the official definition. The law of conservation of energy is that energy cannot be created or destroyed. It can only change form. Another way to think of it, so I'd like you to add this as well, is that the total amount of energy can never change. So when you add up all of the forms of energy, all of the energy stores in a system, it can never change. They always need to add up to the same number. All right, so it can never be destroyed. We can never get more of it. We can never lose any. It always needs to add up to the same amount. So that is the law of conservation of energy. Now we're going to move on to looking to see how this energy can change. So stores and pathways are how energy can change forms. and the different forms it can take. So let's go back to our chocolate bar that we've bought with £5. So the money you used to buy that chocolate bar, so you could have walked into the shop with that £10 note in your pocket. It could have been stored in a bank account, in which case you used a card to buy that bar of chocolate. If you're really technical, you could store it as Bitcoins and find a way to buy it with those Bitcoins. You could meet some friends at school and trade it for something that's also worth the same amount of money as that chocolate bar and do it that way. So it can be stored in all kinds of different ways. All right, the shopkeeper can store it in all kinds of different ways again. The same way that money can be stored in different forms, so can energy. So we have 8 forms of energy stores that you need to know. So we have chemical energy, kinetic energy, gravitational, nuclear, elastic, thermal, magnetic, and electrostatic. So these are the 8 energy stores that you need to know. Something I want you to know as well, that energy can also be in a form that's not in a store. So for example, we can have energy as light or sound, but you can't hold energy in light or sound. All right? But you can have light energy and sound energy that comes off of something or goes into something and becomes another store again. Just want you to keep those in your head. So chemical energy is what we found in fuels or food. So it is actually in molecules is that energy stored. So chemical energy, it's in molecules. So it's released in a chemical reaction, which is why we call it chemical. And you'll learn more about different chemical reactions in chemistry. So kinetic, it's the energy in a moving object. If you run into your mate, if you're walking slowly, you run into your mate, it's very slow. So you don't have a lot of energy. If you're running full tilt and you bump into a mate, you have a lot more energy. So you're moving a lot faster, so you have a lot more kinetic energy. And kinetic energy is one that we will learn more about. Gravitational. I'd like you to add to this, it's gravitational potential energy, which is, we'll learn more about exactly what the word potential means, but it's gravitational potential energy, and it's due to an object height. So a higher object has more gravitational potential energy. Whereas if you lift your pen a little bit, it only has a little bit of gravitational potential energy. If you hold it high above your head, it has more gravitational potential energy. Nuclear energy store is in nuclear reactions. This is the energy stored in the nucleus. Of an atom. So that's the energy between the protons and the neutrons within the nucleus of an atom. Elastic is the stretching or compressing. So this is, you stretch or compress an elastic band, and you can store energy in that way. So that's a spring or elastic. And you'll look a lot more closely at elastic energy in year 11. Thermal energy is the energy in a warm object. All right, so your hot cup of tea, you have that energy coming off of it, you can feel it, that's that thermal energy. Magnetic energy is magnets that are repelling or attracting, because remember, they attract with the opposite poles. And they repel when they're the same pole. And electrostatic, and as I said before, that is the positive and negative charges. So that is the Protons and electrons is often what we talk about there. Moment to try to memorize the energy stores. I want you to pause the video and write down as many as you can without looking. Once you've written down as many as you can, unpause the video and I'll give you a hint for the rest of them. So here's a hint for the rest of them. Seeing if you can get all of these in the order they're in. Pause the video again and we'll go over the answers in a minute. Here are the correct answers for those energy stores. In a hot object, we have our thermal energy store. In foods or fuels is our chemical energy store. Due to object's height is the gravitational potential energy store. Stretching or compressing is the elastic energy store. And a moving object is the kinetic energy store. Separating electric charges, so that's positive and negative charges, is the electrostatic energy store. Nuclear reactions is the nuclear energy store. And separating magnets is the magnetic energy store. So, between the stores, we need a way to get them from one store to the next store. So those are our energy pathways. So our pathway is from one store another. Because remember, our law of conservation of energy states that energy can only move from one store to another. It can't just disappear and it can't just be created. So we need ways for it to do that. So the pathway is how the energy moves between stores. So again, if we go back to our money analogy, so we can exchange money in lots of different ways. We can hand over cash, we can do a bank transfer, you can buy something at a store with a debit card or with a credit card, maybe even with a check. So there's lots of ways that money can transfer from one person to another. The same way energy can transfer from one store to another. So we have mechanical is when a force moves through a distance. So this is when something touches, is a mechanical pathway. Because remember that force is a push or a pull. So when something's touching or when something's forcing something to move is when we have a mechanical energy store or mechanical energy pathway. So this is the most common. An electrical energy store is by charges moving. So this is commonly what we think about as electricity. So when the flowing electrons turns into light energy, for example, that's the electrical pathway. Heating is by a temperature difference. So this is when heat moves from one to the next. So this is reasonably straightforward. Radiation is electromagnetic. So that is light, and this is how energy travels through space. So this is how we get our energy from the sun and everything else like that. So these are the 4 pathways. Again, memorize these. Take a minute, memorize these, and then try to make a list of them on your own. So hopefully now you have the stores and the pathways well in your head. So now I'd like you to go through and give these 2 activities a try. So from the 8 energy stores, which energy stores are in the following? So what is the energy store of a ball rolling along the flat ground, in a bathtub full of hot water, in a cake, and in a stretched bow? Stretched bow for archery. All right, writing those down. And for the pathway, which pathway is used to change the following store? All right, so reading through those, writing them down, pausing the video, writing them down. We'll go over the answers in a minute. So hopefully now you've written down your answers, and we'll correct them now. So a ball rolling along the flat ground, the ball is moving, so it is the kinetic energy store. A bathtub full of hot water. So we know that this is a thermal energy store. A cake is a type of food, so we know that this is the chemical energy store. So again, that bathtub full of hot water, that water isn't moving. It's just sitting in the tub, but it still has that thermal energy. A cake is just sitting on the counter, sitting on the table. It's not moving, it's not doing anything, but yet it still has energy. All right, and a stretched archery bow is the elastic energy store. All right, so double check those and then make sure you have your pathways done as well. So here we have the 4 pathways. So as they jump from the plane, we're touching, we're moving things as a physical force, so that's the mechanical. The chemical store from a battery to the toy car, so that goes through an electrical circuit. From the battery to movement, that's electrical. Radiation, because it's going through space. And the thermal store, so we're dealing with heat. So it's from a thermal store to a thermal store, it's simply heating. So some last little questions here. So finish up this knowledge check and then give a go to these application of knowledge questions. Again, pause the video, we'll go over the answers in a minute. We have the correct answers for the knowledge check and the application of knowledge. Question 9 and 10 did come from a different topic. So the states of matter, we have solid, liquid, and gas, and the particles are far apart in a gas. If you couldn't remember those, make sure you go back and revise the states of matter. Ask your teacher if you need help with that. Don't forget gravitational potential energy, not just gravitational energy. And for the application of knowledge questions, anything that's high can work for question 1. So I have a book high on a shelf, but anything that's high up will work. So for question 2, anything that's moving, for example, a car on a road. Because it does say give an example, you need to give some kind of example. It doesn't matter what that example is, but an examiner would need to know that you do understand what that thing is. And an example of a thermal store, so anything warm, so a hot cup of tea or a cup of hot cocoa or whatever, bowl of soup, a radiator that's on, anything like that. If you have any questions about the topic, remember to email your teachers about it, and don't forget to do any quizzes or any assignments that your teachers have set.